In this lesson, you will learn how to determine the moment of a force about a certain point, both in 2-dimensional and 3-dimensional scenarios. Our first question is a 2D case where we have a structure shown on the left that has a fixed support at point A and a free end at point B. So this is a frame where we have three forces, F1, F2 and F3 applied at different points on the structure. So the question asks, determine the moment of each of the three forces about point B. So for F1, right, let's draw the force diagram for F1. Here the force F1 has a magnitude of 250 newtons, and this has to be resolved into both its vertical and horizontal components. That is typically the technique that we will use to solve two-dimensional problems. We take moments not of the original force about the point, but using its components. So the vertical component is shown by this vector in orange color. The magnitude of this orange component is 250 cosine 30 degrees, where 30 degrees is the angle that the original force makes with the vertical. The horizontal component is directed in this positive x direction, and the magnitude is 250 sine 30 degrees. Now that we have resolved the original force into both its vertical and horizontal components, we can determine the moment of this force F1 about the point B. So for F1, we take positive in the anti-clockwise direction. Moment about point B is equal to, first we look at the vertical component, 250 cosine 30 degrees. So what is the moment arm? Shown here is the line of action of the vertical component as a dashed line. Now the moment arm of this vertical component to the point B is actually this horizontal distance here, which is given by 3 meters. So we put here times 3. And then now let's consider the horizontal component. Horizontal component is 250 sine 30 degrees, and it is going to bring about a clockwise moment about point B, right? So this horizontal component is pointing to the right, so you can imagine that this horizontal component is going to rotate the structure clockwise. So it is negative because our convention is that positive is anti-clockwise. So it's negative 250 sine 30 degrees times, so what is the moment arm in this case? Now shown here in the figure is a certain dashed line, which is the line of action of the horizontal component. We can see that the perpendicular distance from this line of action to the point B is actually 4 meters. So we multiply by 4. So if you would compute this sum, you will find out that the final answer is 149.51, not forgetting the units, Newton meter. So that is the moment of force F1 about point B. It is important to note that the moment here is positive, which means that it is in the anti-clockwise direction as we had assumed earlier. Now we move on to force F2. F2 is applied at this corner here at a certain angle 60 degrees to the horizontal. So in this figure here, the force F2 is drawn as a vector and has a magnitude of 300 newtons. We are going to resolve into both its vertical and horizontal components. The vertical component is shown here, alright, pointing downwards, and it has a magnitude of 300. In this case, because this is 60 degrees, so there will be 300 sine 60. And the horizontal component is pointing to the left in the negative x direction, and it has a magnitude of 300 cosine 60 degrees. So now we try to sum up the moments of F2 about point B. So we still take positive as anticlockwise. Moment about point B is equal to, first we look at the horizontal component, which is this component here. It's pointing to the left, which means that it is going to bring about an anticlockwise rotation about point B, therefore it is positive. So 300 cosine 60 degrees. What about the moment arm? Look at the figure here on the left. The perpendicular distance from the line of action of this horizontal component, and point B is actually 4 meters. So multiplied by 4. What about the vertical component? Now the vertical component has a line of action that cuts through point B. Therefore, there's no movement here. So the final answer is just 600 Newton meter. For force F3, we realize that the line of action of F3 cuts through point B. Therefore, the moment arm is 0 and there's no movement of this force about point B, meaning that for F3, moment about B is just 0. Okay, so we have finished our example for a two-dimensional scenario. Next, we'll move on to a 3D scenario. Alright, now we shall learn how to determine the movement of a force about a certain point in a three-dimensional setting. In this question, we are supposed to determine the resultant moment produced by forces Fb and Fc about point O. So Fb is this force here, and Fc is referring to this force here pointing from A to C. And point O is here at the bottom of the post. Alright, express the result as a Cartesian vector. So this is a three-dimensional question. First, we write down the formula that computes the moment of a force about a certain point in its vector notation. So it's m naught, meaning that moment about point O, which is what the question wants, is equal to the moment arm ROA cross FC. Now ROA is just the moment arm pointing from O to A, and FC is actually this force vector here. And we have another force plus ROA once again, because this force FB shares the same moment arm as force FC cross FB. Now, the moment arm OA by point A can lie on any point on the force vector or on the line of action of the force vector. We can of course choose also OB. Right, for the case of force FB, we can also choose OB, and for the case of FC, we can also choose OC. So in other words, we can also compute the moment as ROC cross FC plus OB, so ROB cross FB. Both will give you the same answer. So for simplicity, we will just use the first formulation, right, where the moment arm ROA is just pointing vertically up, so there's only one vertical component, and same thing for the ROA for force FB. So the first thing we need to determine is to express our vector FC and FB in vector notation. So we start off with FC. We know that any vector can be expressed as its magnitude multiplied by its unit vector. In this case, FC is a vector pointing from A to C. So the unit vector is UAC, kept to indicate that it is a unit vector. So we are given that FC has a magnitude of 420 newtons. So we put it here, 420. And then here we are going to compute our unit vector UAC. Now for this AC moves in the positive x direction by 2 units. So we put down here 2i. And it also moves in the negative y direction by 3 units. So minus 3j. It moves downwards in the negative z direction by 6 units. So minus 6k. And what comes below is actually the magnitude of this vector AC, which is just 2 squared plus 3 squared plus 6 squared. Right, if you were to do this, you end up with 420 2i minus 3j minus 6k over 7. Now at this point, instead of calculating the multiplications one by one, I'm going to use our Casio class width to compute this scalar vector multiplication. So this is our class width Casio MX991EX emulator. First, we need to enter this vector 2i minus 3j minus 6k into the calculator. What we will do is we go to menu and then go down to vector option, press 5, and then we define a certain vector, vector A. Dimension is 3 because there are 3 elements in this vector. It's a 3-dimensional case. The first element is 2 equal minus 3 equal minus 6 equals. So now that you've entered the vector, go to option and then click on 3, vector calculation. Alright. So you access the vector through options again, then select vector A, multiplied by, in this case, 420 over 7. So 420 over 7 equal. So we can see that the first component is 120, the second component is minus 180, third component is minus 360. So we just enter the answer here, equal to 120 I minus 180 J minus 360 K. Not forgetting the units is in newtons. We are going to do the same thing for our force FB pointing from A to B. So the same procedure applies. FB vector is equal to the magnitude FB multiplied by the unit vector UAB cap, once again to indicate that it is indeed a unit vector. So that is equal to, given that the magnitude is 780 newtons, 780, then multiplied by the unit vector in the AB direction, which in this case, look at the x component, it is not moving in the x direction at all, so it's 0i. In the y direction, it moves 2.5 meters positive, so plus 2.5 j. And finally, in the z direction, it moves downwards by 6 meters, so it's minus 6k. And then once again, we have to divide by the magnitude, which is just, in this case, 2.5 squared plus 6 squared. Alright, if you were to use your Casio calculator again to compute this, you should be getting 300 J minus 720 K newtons. Now that we have obtained the vector form of the forces Fc and Fb, and we also have the formula to compute the moment about point O of these two forces, we also have chosen our moment arm to be position vector ROA, so we can go on to compute the moment about O. So in this case, we can use the determinant expression. So with I, J, and K. Now the position vector ROA actually is just 6K, right? So there's no X and Y components, but there's a positive 6 Z component, and this force FC is 120 minus 180 minus 360. So just put it down here, negative. And for the other cross product, we do likewise. ROA is still 006. FB is 0, 300 minus 720. In this case, you can also use a calculator to compute the determinant, but because both x and y components in the middle row are 0, so to compute this is really not that difficult. But nevertheless, I will show you how you can use a class width calculator to compute the determinant. We first define the position vector ROA 006. So we define vector and we store this into a vector A. So dimension is 3, 0, 0, 6. Alright, then we define the force vector FC. Alright, we store this into vector B, which is option 2, 3 dimensions. So it's 120 minus 180 minus 360. And then we define our last vector FB. We store this into a vector C, which is option 3, 3-dimensional, which is 0, 300 minus 720. Okay, then option, what we can do now is to compute the cross product. So we choose 3, vector calculation. In this case, we first select our position vector ROA, which is stored in a vector A, which is option 3. Cross product, we just input multiply, and then the vector FC is stored in vector B, remember? So vector B is option 4. So that will give us the result for this determinant calculation. Alright, because this determinant essentially determines the cross product of ROA and FC. So you have here 180i plus 720j plus 0k. So we write down here 1080i plus 720j, right? And then there's no k component. So for the other determinant or for the other cross product, we come back to our class width calculator, and then we go back to option, and now we use choose vector A again, our moment arm ROA, and cross FB. Remember, FB was stored in our vector C, which is option 5. So that will give us the answer minus 1800i, and no j and no k components. So it's just minus 1800i. So plus minus 1800i. And if you add these two up, you will get minus 720i plus 720j Newton meter. Alright, so that's our final answer. This is a 3-dimensional example, so everything is in vector formulation, including the way we express the force vectors, the way we express the moment arms. Now compare this with the previous 2-dimensional example. We merely use the components to compute the moments because it is actually much easier that way for 2-dimensional setting. But for 3D case, you have to use the full machinery of vector algebra to do it. So we have finished the 2 examples for today's lesson. Once again, today's lesson is about determining the moment of a force about a certain point. I've done this for both a 2-dimensional and a 3-dimensional case. Hope you enjoyed the lesson. See you